Welcome back. This is sequence 5 of the course, and we will look more precisely at the OCaml language now, getting some little overview, a glimpse of the language to see how it looks like. Let's take the tour. So the objective of this sequence is really just to present you some examples that showcase some of the advanced features of the OCaml language. You remember, the users told us what they like is safety because of strong static typing, pattern matching, conciseness because of polymorphic typing and type inference, expressiveness from higher order functions. So let's look at some examples that show short sequences of code with these features. Little disclaimer, first of all, this is just a quick tour to give you an example and a taste of the language, so you are not expected to fully understand the example right now. Now, just carry on with us a bit. Of course, you will understand everything and much more than this at the end of the course. So, hold tight and let's go. So, let's start by meeting the list data structure. This data structure is built in OCaml, it is predefined, you have special syntax for this. So, in particular, this square brackets, open and close, is just a representation of the empty list, and this A, colon, colon, L is a list that contains A as the first element and L as the rest of it. And of course, you have already seen an example where if you put elements inside the list, that's a list with a few more elements in it. Let's write a function now to sum all the elements of an integer list. How could you write this? Well, let me do it for you. So we define a function which is called sum L, sum of the element of the list, and we use what is called pattern matching to define the function by cases. We say if the list that has been given to me is empty, then the result will be 0. Else, if it is not empty and it has the shape of having a first element and the rest, then the result will be taking the first element and adding it to the result of summing the element of the rest of the list. Okay, so it doesn't matter if you really don't understand what is going on, it's a very simple definition. What is really important to notice here that we did not declare any type in our code. We didn't say what is the type of A, what is the type of rest, what is the type of sum L, nothing. And yet, as soon as you hit enter here, well, the system answers you with this message. It says, thanks a lot, you defined a value which is sum L. This is actually a function that takes an integer list and returns an integer. Okay. So the OCaml type checker has inferred for us the good type of this program for free. We had nothing to do. And these types, which are inferred by the compiler, are actually computed and enforced at compile time, not at execution time. Let's see an example. For example, if I use this sumL function to sum the element of the list that contains 1, 2, and 3, where the compiler computes the result and says, yes, the result is an integer and its value is 6. That's correct. But let's make, on purpose, a mistake. Okay, now I'm going to apply this function that should work only on integer list. I try to cheat the system and pass it not an integer list, but a list of strings that contain integers. Let's see what happens. Well, the system answers by saying, stop, there is an error. This particular expression here is a string, but we were expecting an integer. Why? Because sumL is waiting for an integer list. I found the list, but not of integers, of strings, so this is an error. And no code was executed up to now. This is just during the compilation phase. During the compilation, the types are checked. And actually, this is a very small example, you will see this more in details later on, of a fantastic property which was defined by Robin Milner for the ML class of languages. He really wanted to make sure that well-typed programs cannot go wrong. I mean, type errors do not show up during the execution. They are catched by the compiler, by the type checker. If you pass the compiler type checker, you will not have type errors at execution. Well, so we have written our nice function, sumL, that sums up the element of the list. But if you look at the code, actually, I mean, this 0 here and plus there, well, they can be just parameter of the function, just keeping the same structure of the function here. So let's try to turn them into parameters and see what happens. So I will rewrite the function, give it a new name. Let's call it fold now. It has 2 extra parameters, op, which will play the role of this plus operator here, and E, which is play the role of the result returned for the empty list. Okay, so it's again definition of the function. It is defined by cases. On the empty list, instead of 0, I will return this e here. And on the non-empty list here, you remember here I was taking a plus the result of recursive call of the function. Here I will apply the operator op to a and the result of the recursive call. Okay? So basically it is exactly the same structure of the function, but I have turned op and e into parameter of the new function fold. But again, here we did not declare any type in our code. We didn't say what is the type of fold, didn't say what is the type of op, didn't say what is the type of e. And yet the compiler reads the program, accepts it, and tells us, thanks a lot, you defined the fold function, and look, I believe that what you have given me, actually I don't believe, I'm sure, what you have given me is a function that takes a parameter op, that takes an argument of type A, another argument of type B, and gives a result of the same type B, then expects an argument of type B, our E here, then takes a list of elements of type A, I mean this list here, and gives back a result which is again of type B, which is type of this E, for example. Well, I'm not sure you're really convinced that this is the right type. This will become clearer over the course, but what is important is that this is actually the most general type one can give to this function, and the OCaml type checker just inferred it for us, the most general type, for free. We had nothing to do to get it. And once you have a function of this general type, you can apply it to many different situations without changing the code. So let's do it. Okay? So now I'm using this fold. The operator is the sum. The value for the empty list is 0. I apply it to the list 1, 2, 3, 4, 5. This, unsurprisingly, will compute the sum of all the elements of the list, which is, you see, 1 plus plus 3 plus 4 plus 5. This makes 15. And actually, the system tells us, OK, the resulting list in integer and value is 15. But now imagine you want not to add all the elements of the list, but multiply them. Well, you use the same function fold. Now the operation is a multiplication, and for the empty list you just return 1. You call it, and this multiplication of this list here is just factorial of 5, which is 120, and this is the result you're getting. But then you can decide to use a function in another environment too. For example, you can decide to concatenate all the strings in a list using this, which you will discover is a concatenation operator for list. And for the base case, I return the empty list. So concatenating the string with 1, the string with 2, the string with 3 should return us a string with 1, 2, 3, which is exactly the case. And then you can do more complicated stuff. Like, for example, here I have a list of pairs, and I would like to compute the sum just of the first elements of each of the pairs. I mean, see, here it would be 2 plus 3, which is 5. Again, I use the same higher order function fun, and here as combination operator, I tell the system I will take a pair and the value A and add A with the first element of the pair. And 0 is returned for the first element. And of course, the system gives you back 5, which is exactly the sum of 2 and 3. And these are toy examples, but as you have seen, you have a general function with a very general type. It can be applied to different type and data structures. The type is checked and is safe. You will never have a type error. And it provides big flexibility. You have written your code once and you specialize it to different situations without need of using any kind of boilerplate. Okay. So that was the first example. Well, okay, so now let's turn to pattern matching. We have got an idea what pattern matching is in the example before, but why is it so powerful? Why people love it? Well, let's write a function, another example to see this. Let's write a function that removes all duplicates, consecutive duplicates from a list of elements. Okay, and the good name is destutter. I mean, stuttering is stuttering, so remove stuttering from a list of elements. It will be a function again. So if the list that is given to me is empty, but there is nothing to do, I write on the empty list. If the list had at least 2 elements here, x and y, I mean, that's the interesting part of the story. I need to remove a y if it is the same as x. Okay? So what happens? If x and y are equal, then I drop the x and keep on working on the list that contains only y and the rest. Okay, so I remove the first duplicate. Otherwise, if x and y are different, well, I need to keep the x and keep on working on the rest of the list. This seems a very sensible operation to do. Up to now, it seems a complete function, should work. Well, let's pass it to the compiler and see what happens. Here we get a warning. The compiler is telling us, look, the definition you have given has no type errors. I have well understood you are defining a function from lists to lists, of course a polymorphic function. But I'm not happy because your definition by cases here, this pattern matching, is not exhaustive. What does it mean? It means that there is at least one case that I didn't cover. And the compiler tells us what is an example of these cases I'm not covering. Here is an example of the value that is not matched. A list that has something as a first element and nothing less at the end. So this basically is a list with just one element. Well, he's right. I have handled the case of an empty list, the case of a list that has at least two elements, but I forgot to say what happens if I have a list with just one element. Okay? So the compiler is telling us which case we missed, and we can follow its advice by completing the definition, adding the handling of that particular case there. So let's do it again. So for the empty list, I do nothing. For the list that has just one element, I need to say what happens. And what happens in this case? Well, if a list has just one element, there is no stuttering, so there has nothing to do. I write on the same list as it is. And the last clause is the same as before. Now the compiler is happy and say, okay, all cases are covered. You have defined a function which is well typed, takes lists to lists, and we can test it. Okay? So let's try to apply it to this stuttering, this list where you have many, many consecutive duplicates. Well, since I didn't make any mistake in this program, you see you have this list here where all consecutive duplicates have been collapsed into single value, and it is actually an integer list. But again, remember the type of this? This stutter now can be used on any data structure, not just integers. Okay? Any list or something, not just lists of integers. Well, that was a very quick tour. Okay? Just a glimpse of OCaml language and pictures, and much more is in store for you in the rest of the course, but I do hope you are starting to get the feeling of why this language is so concise, efficient, safe, as the user told us.